The internal resistance of a 2.1 volt cell which gives a current of 0.2 amperes through a resistance of 10 ohms is. We have four options: 0.5 ohms, 0.8 ohms, 1 ohm and 0.2 ohms. Let us look at the basic formula. EMF equals current into external resistance plus internal resistance. Here we need to find out the internal resistance of the cell. So substituting the values, we get 2.1 equals 0.2 amperes, external resistance of 10 plus the internal resistance 0.2, we get 10 plus R. Therefore, this is 10.5 equals 10 plus R. Therefore, the internal resistance is 0.5 ohms. That is option 1. Option 1 is the correct answer. If N is the number of free electrons in a metallic wire, then the resistance is proportional to. Let's look at the formula for resistance. V equals IR. Therefore, resistance here is inversely proportional to the current. And the formula for current, Q equals IT. So I over here, current, is proportional to the charges, which is the number of electrons over here. So I is directly proportional to N, and since I is directly proportional to N and R is inversely proportional to I, therefore R should be inversely proportional to N. Therefore the answer over here which we get is option 2, 1 by N. A wire is cut into 4 equal pieces which are put together side by side to obtain one conductor. If the original resistance of the wire was R, the resistance of the bundle will be, we have 4 options: R by 4, R by 16, R by 8 and R by 32. Since the initial resistance of the wire was R and the formula for resistance R equals rho L by A, here R, that is the resistance, is directly proportional to L and inversely proportional to the area of cross section. Now when the wire is cut up into 4 pieces, the length is divided by 4, that is, so the next resistance or the final resistance would be R by 4. However, since they are placed side by side, which is nothing but these are the 4 parts and each has a resistance of R by 4, and when stacked together the total area of cross section becomes 4 times the initial, and since R is inversely proportional to A, therefore the new resistance R dash would be R by 4, since the length has been shortened by 1/4 and also it becomes 4 times A. So R dash is equal to R upon 60. Therefore the final resistance is R by 16, which is option 3. Therefore option 3 is the correct answer. A wire of resistance 4 ohms is stretched to twice its original length. The resistance of the stretched wire would be, let us look at a wire. Okay, this is the area of cross section and this is the initial length. Now since the wire is extended to twice its original length, the area of cross section would reduce when the length increases. Here we need to note that the initial volume is equal to the final volume. Therefore initial volume, area times the length, equals the final volume, area times the new length. So the question says that the final length is twice the initial length, A dash into 2 times L. So the final area is A by 2. Let's look at the formula for resistance, that is R equals rho L by A. So R dash would be rho times L dash, which is nothing but 2 times initial length upon the area A dash, which is A by 2. So R dash would be rho L by A into this 2 and again this 2 would come into the numerator, which is initial R value into 4. So this initial R value is 4 ohms. So R dash would be 4 into 4, which is 16 ohms. 16 ohms, that is option number 3. Therefore, option 3 is the correct answer. The velocity with a free electron in a conductor gets drifted under the influence of applied electric field is. We've got 4 options: average velocity, drift velocity, thermal velocity, and critical velocity. For a conductor, electrons are flowing in random directions when there's no potential difference applied. But when a potential difference is applied across the terminals, an EMF is generated, an electric field is generated, and hence all the negative electrons start flowing towards the positive terminal of the battery. This flow of electrons is known as drift velocity. Hence option 2 is the correct answer. The difference of potential between the terminals of a cell in an open circuit is called. There are 4 options. First, resistance. Second, capacity. Third, electromotive force. And fourth, potential difference. Now, since this circuit is open, so it is nothing but a battery that we are measuring the potential across. So the potential difference, the potential between the terminals in an open circuit is nothing but the electromotive force, that is the total amount of energy which the battery can use to supply electrons around the entire circuit. And in an open circuit, this is known as the electromotive force. So option 3 is the correct answer. In the diagram below, each resistance is of 1 ohms. The total resistance between A and B is. Now each of these resistances of 1 ohms, we can simplify this circuit as this is point A and this is point B. So this terminal is directly connected to B. This is again connected between A and B. This resistance over here is also connected between A and B, whereas this resistance also is connected between A and B. So as you can see, all the 4 resistances are in parallel to each other and each having a resistance of 1 ohm. So 4 resistances parallel to each other having 1 ohm resistance each. So the effective resistance would be 1 by 4 ohms. The option given here is 2 by 8, which is nothing but 1 by 4. See, option 3 is the correct answer. In the diagram shown here, potential drop across 3 ohm resistor is, we've got 4 options: 1 ohm, 1 volt, 1.5 volts, 2 volts and 2.5 volts. In order to find out the potential difference across this resistor, what we need to do is find out the total current in the circuit. So I is equal to V upon R. I equals the potential 3 upon the external resistance to the circuit, that is 4 ohms in series with a parallel combination of 3 volts, 3 ohms and 6 ohms, which is nothing but 3 into 6 upon 3 plus 6. So 3 upon 4 plus 2. 3 upon 6, which is 0.5 amperes. So the current in the circuit is 0.5 amperes. Now let's look at the potential difference across this terminals. What we need to know is that the potential difference over here and over here, the potential difference across the 3 ohm resistor and the 6 ohm resistor would be the same since they are connected in parallel combination. So the effective resistance of this parallel combination is 3 into 6 upon 3 plus 6, which is 2 ohms. So the potential difference across the combination is I into R, which is 0.5 amperes into 2, which is 1 volt. So option 1 is the correct answer. The magnitude of current I in the following circuit is, let us simplify the circuit. This is a 30 ohms resistor in series with another 30 ohms resistor, and these two are in parallel combination with another 30 ohm resistor. These two series resistances of 30 ohm makes up 60 ohms and in parallel with 30 ohm resistor. So the effective resistance is 60 multiplied by 30 upon 60 plus 30, which is nothing but 20 ohms. In order to find out the current flowing through the circuit, we use the formula V equals I times R. V is given as 2 volts. The current is what we need to find out, and R of 20 ohms. Therefore, I is equal to 2 upon 20, which is 1 by 10 amperes. So option 3 is the correct answer. How many dry cells, each of EMF 1.5 volts and internal resistance of 0.5 ohms, must be joined in series with a resistor of 20 ohms to give a current of 0.6 amperes in the circuit? We have 4 options: 2, 8, 10 and 20. Let us look at the circuit diagram. Since we don't know the number of cells, let's just, these are, suppose there are n number of cells with each of internal resistance of 0.5 ohms, and this circuit is connected to an external resistance of 20 ohms. The current which is flowing through the circuit is 0.6 amperes. So when the EMFs are connected in series, they add up. In the similar manner, when resistances are connected in series, they also add up. So let us use the basic formula E equals I times R plus R. But here, since there are n number of EMFs, so the formula would change as n times E equals I times R plus n times internal resistances. So n into EMF of 1.5 is equal to 0.6 amperes into external resistance of 20 plus n times internal resistance of 0.5. So solving this, 1.5 times n upon 0.6 is equals to 20 plus n by 2. Therefore 1.5 times 0.6 n minus n by 2 equals 20. Therefore what we get here is 2n is equals to 20. Therefore n equals 20 by 2, which is 10. So therefore 10 cells needed to be added in series. So option 3 is the correct answer. A battery of EMF 10 volts and internal resistance of 0.5 ohms is connected across a variable resistance R. The value of R for which it delivers maximum power is, the formula for power is V square upon R, plus there is an internal resistance R to the circuit. What we need to understand is the value, since the value of EMF isn't changing, there is an external resistance R which is in our control. When R is minimum, the power would be maximum. So in order to choose the correct answer, let us select the value of R which has the least value, which is 0.5 ohms. So when R would be 0.5 ohms, the current in the circuit would be greater, which directly translates to power, which would again be greater. Hence option B is the correct answer. The potential difference between the points A and B for the circuit diagram shown below is We got four options: 2, 6, 4 and 8. In order to find out the potential difference, let us simplify the circuit and find out the equivalent resistance. The 6 ohm resistor and another 6 ohm resistors are in parallel, so which gives us a combined resistance of 3 ohms. This is in parallel with another resistance of 3 ohms and in series with 2.5 ohms. The current flowing through the circuit is given as 2 amperes. The 3 and 3 parallel combination gives an effective resistance of 1.5 ohms in series with 2.5 ohms between the points A and B. Now if you look, the effective resistance now becomes 4 ohms and the current flowing is 2 amperes. Therefore, the potential difference V equals I times R can be written as 2 into 4, that is 8 volts. So option 4th is the correct option. Potential difference between the point A and B in the diagram when switch is open is, we've got four options: 36 volts, 9 volts, 12 volts and 0 volts. Now when this switch S is open, this arm AB becomes ineffective. So we can neglect it and draw the circuit as 3 ohms, 6 ohms, again 6 ohms, 3 ohms, and this is connected across a potential of 36 volts. 6, 3, 6, 3. So the effective circuit can be drawn as 9 ohms, since 3 and 6 are in series. Similarly here 9 ohms, and this is connected across 36 volts. Now the potential difference across these 2 points is 36 volts. Therefore the current flowing through each arm, V equals I times R. Therefore current flowing through each arm is 36 upon 9, which is 4 amperes. Since current flowing through each arm is 4 amperes, so a current of 4 amperes flows through here and similarly 4 amperes through here. To find out the potential at this point and this point, that is points A and B, we'll find out the potential at A with respect to ground and potential at B with respect to ground. So potential at A with respect to ground, V equals IR, that is 4 amperes into 6 is 24 volts. Similarly at B, we get 4 into 3, which is 12 volts. So potential difference across AB is 24 minus 12, which is 12 volts. So option number 3 is the correct answer. An electrical circuit is shown in the figure. The potential difference across the resistor of 400 ohms measured by the voltmeter of resistance 400 ohms is, let me simplify this circuit before we solve the sum further. There's a 10 volt potential and this is connected to 100 ohms. Again this 100 ohms. There's a 100 ohms over here. This 400 ohms and this 200 ohms. And this is again in parallel with 400 ohm voltmeter. So as you can see, it forms a Wheatstone's bridge. This is 100, 100, 200, 400 and 400 again. So the 400 and 400 in parallel form an equivalent resistance of 200 ohms. So as you can see, 100, 200, 100, 200. The bridge over here is balanced, which means no current flows through this arm. Since the bridge is balanced, therefore the current flowing through each arm will be calculated as I is equals to 10 upon the effective resistance of each arm, that is 100 plus 200, is 300. So the current flowing through each arm is 1 by 30 amperes. Now since the potential across the 400 ohm resistor is to be found out, since the effective resistance is 200 ohms, so V equals I times R, that is 1 by 30 times. We need to write the effective resistance because the potentiometer, I mean the voltmeter, also gives its effective resistance of 400 ohms. So the effective parallel resistance, that is 200 ohms, needs to be applied. 6.67. Therefore, option number 4, 6.67, is the correct answer. The steady state current in the 2 ohm resistor, if internal resistance of the battery is negligible and the capacity of condenser is 0.2 microfarad, is, we've got 4 options: 3 amperes, 6 amperes, 0.9 amperes and 0.75 amperes. Now what we need to know here is that since the steady state current is being mentioned, we need to know that the capacitor does not operate in steady state. That is, it acts as an open switch when steady state potential or steady state current is flowing through the circuit. Therefore, this arm becomes nullified. So the circuit now transforms into a 2 ohms resistor in parallel with a 3 ohms resistor, and it's in series with a 2.8 ohm resistor. So the effective resistance of 2 ohms parallel with 3 ohms is 1.2 ohms. So the total resistance in the circuit is 1.2, 2.8 across a 6 volts battery. So the total resistance is 4 ohms. So the current flowing through the circuit, I, is equals to 6 upon 4, which is 1.5 amperes. Now since the current flowing through the entire circuit is 1.5 amperes, let us find the potential difference across the parallel arms. So I equals V upon R. So V equals current I into the effective resistance of the parallel arms, which is 1.2 ohms. Let us keep this value this way, and now we know that since the potential difference across the parallel arms is 1.5 into 1.2 volts, so the current flowing through the 2 ohm resistor would be I equals V upon R, which is nothing but 1.5 into 1.2 upon 2. So I over here becomes 0.6, and 0.6 into 1.5 is 0.9 amperes. Therefore, option number 3 is the correct answer, 0.9 amperes. A thick wire is stretched so that its length becomes 2 times. Assuming that there is no change in density, what is the ratio of change in resistance of the wire to the initial resistance of the wire? Since there is no change in the density, we need to know that the volume of the wire remains constant. That is, A1 into L1 equals A2 into L2. Now L2 becomes twice L1, so A1 L1 once A2 to 2 times L1. Therefore, the final area A2 is A1 by 2. Now the formula for resistance R equals rho L by A. Therefore, R2 would be rho times L2, which can be written as L1 into 2 upon A2, which can be written as A1 into 2. So rho L1 into A1 can be written as R2 equals R1 times 4. So the change in resistance, so R2 is 4 times R1. So the change in resistance is 4R1 minus R1, which is 3R1. So there's a change of 3R1 and initial resistance is R1. So the ratio is 3:1. So option number 3 is the correct answer. two resistance wires on joining in parallel have a resultant resistance of 6 by 5 ohms. One of the wire breaks. The effective resistance is 2 ohms. The resistance of the broken wire was, let us draw two wires of unknown resistances R1 and R2 in parallel combination. So the effective resistance now would be R1 into R2 upon R1 plus R2, which is given a value of 6 by 5 ohms. Now when one of the wire breaks, the circuit consists of only one resistance R1, and which is given as 2 ohms. So substituting 2 ohms as the value of R1, we get as 2 times R2 upon R1, 2 plus R2 is equals to 6 by 5. 2R2 is equals to 12 by 5 plus 6 by 5 times R2. Therefore, 2 minus 6 by 5 R2 is equals to 12 by 5. 4 by 5 R2 equals 12 by 5. Therefore, R2 equals 3 ohms. So, option number 2 is the correct answer. In the following circuit diagram, find the unknown current I through the circuit. In order to find out I, we will apply junction law, Kirchhoff's junction law, at the point C. So Kirchhoff's junction law says that the amount of current flowing into the junction is the same as that leaving the junction. And current flowing into the junction is taken as positive and leaving the junction is taken as negative. So the current I which flows into the junction C is nothing but 1 plus 2, which is nothing but 3 amperes. So option 3 is the right answer. Using the circuit diagram from the problem, what will be the EMF of the cell E? In order to find out this EMF, let us apply Kirchhoff's voltage law for the loop FCDE. FCDEF. Let us apply Kirchhoff's voltage law for this loop. Now in this loop, there is an EMF cell E, 1 ohm resistor with current of 1 amperes flowing through it, and there is a 2 ampere current flowing through a 3 ohm resistor. So the Kirchhoff's voltage law, if when you assume current flowing in the clockwise direction, can be written as E. Since there is a potential drop across the battery, so it would come as negative, and for the resistance of 1 ohm, the current is flowing from a higher potential to a lower potential, but in the direction of the consideration there is a rise in potential. So plus 1 ohm into 1 amperes. For 3 ohm resistor, the current over here is flowing from higher potential to a lower potential. So there is a drop in potential. So minus 3 ohms into 2 amperes is equals to 0. So this can be written as minus E plus 1 minus 6 equals 0. Therefore, E becomes minus 5 volts. So option number 4 is the correct answer. The bridge is maximum sensitive when all the 4 resistances are, we've got 4 options: different order, same order, partially same order, partially different order. So we need to know that in a meter bridge, as we know that the resistance or the accuracy is greatest when the balancing point is obtained between the 1/3 of the length of the wire, in the middle 1/3. So this is possible when these two resistances, in fact when all the resistances are of a similar order, and when they are similar, the balancing point is obtained in between or the middle 1/3 of the wire, and hence the answer should be same order. The equivalent resistance between A and B in the adjoining figure is 1 ohms. What is the value of middle resistance? we have 4 options: 9 ohms, 1 ohm, 6 ohms and 3 ohms. In the figure, 1 ohm and 2 ohm resistances are in series, and again 1 ohm and 2 ohm resistances are in series. So the circuit can be drawn as 3 ohms, unknown value, and again 3 ohms. Total resistance between A and B is given as 1 ohms, and there are 3 resistances which are parallel. When there are resistances parallel, and if they are of equal magnitude, the equivalent resistance becomes the resistance in parallel divided by the number of times they are in parallel. Since there are 3 resistances and 2 of them have 3 ohms, it is natural that the third resistance also should be 3 ohms, so as to give an effective resistance of 1 ohm. Hence, the unknown resistance value should be 3 ohms, which is option number D. In the circuit shown below, the current flowing from the battery is, as you can see, a Wheatstone's bridge is formed, and since the balancing condition, that is R1 upon R2 equals R3 upon R4, this condition is satisfied since all the arms have equal resistances. Therefore, the bridge is balanced. Now, since the bridge is balanced, no current flows through this middle 2 ohm resistance. Hence, the circuit can be reduced as 2 ohms resistance in series with 2 ohms resistance, and the parallel combination of 2 ohm and 2 ohm resistances again. So 2, 2, 2 and 2. This can again be simplified as 4 ohm resistance in parallel with 4 ohm resistance, and the parallel combination gives an effective resistance of 2 ohms. Now therefore the total effective resistance is 2 ohms and a battery of 2 volts is there. So the current flowing through the circuit is I upon V upon R, which is nothing but 2 upon 2, which is 1 ampere. Therefore option number 2, 1 ampere is the correct answer. The resistance of 4 arms P, Q, R and S in a Wheatstone's bridge are 10 ohm, 30 ohm, 30 ohm and 90 ohm respectively. The EMF and internal resistance of the cell are 7 volts and 5 ohms respectively. If the galvanometer resistance is 50 ohms, the current drawn from the cell will be, there are 4 options: 0.2 amperes, 0.1 amperes, 2 amperes and 1 ampere. In order to continue further, let's draw the cell. Since there is a 10 ohm resistor, 30 ohm resistance, 30 ohm resistance, 90 ohm resistance and a galvanometer having a resistance of 50 ohms connected across a battery of 7 volts and 5 ohms internal resistance. Now in this circuit, 10 upon 30 is equal to 30 upon 90, and this is the balancing condition. Since the condition is satisfied, the bridge is balanced, and hence no current flows through the galvanometer arm, and hence this 50 ohm resistance can be negated. So the circuit can be reduced as 10 ohms in series with 30 ohms and the parallel combination of 30 ohms in series with 90 ohms. So the circuit is 40 ohms in parallel with 120 ohms. So the total effective resistance is 40 into 120 upon 40 plus 120, which turns out to be 30 ohms. So the effective resistance is 30 ohms. So the current I is nothing but V, which is 7 volts upon 30 plus 5. 7 upon 35, 1 by 5. So 1 by 5 is 0.2 amperes. So option 1 is the correct answer. In a balanced Wheatstone's bridge circuit, the current through the galvanometer is 0. The current through the galvanometer will not be 0 when there are 4 options. The battery EMF is 0, the battery and the galvanometer are interchanged, all resistances in the circuits are doubled, resistances of adjacent sides are interchanged. Let us draw a meter bridge, a Wheatstone's bridge. In this, the balancing condition is R1 upon R2 should be equal to R3 upon R4. Now when R1 and R3 are interchanged, there is a possibility that R3 upon R2 would not be equal to R1 upon R4, and due to this the bridge may not be balanced, and hence the galvanometer arm would have some current flowing through it, and hence the option D is the correct answer. When the resistance of adjacent sides are interchanged, the galvanometer current would not be zero. In meter bridge, X and 2X resistances are connected in left and right gap respectively. The null point is obtained at, there are four options, 33.3 centimeters from the right end, 33.3 centimeters from the left end, 66.6 centimeters from the left end, and 40 centimeters from the left end. Let us draw a meter bridge. A resistance R is connected in the left gap and 2R or 2X is connected in the right gap. And this is 100 centimeters. For a balancing point at a length L, the balancing condition or the bridge is said to be balanced. In this case, the meter bridge is said to be balanced when R upon 2R would be equal to L upon 100 minus L. Therefore, the balancing length L can be written as 100 minus L. Therefore, 3L equals 100. Therefore, the balancing length L is equal to 33.3 centimeters. So, from the left end, it is 33.3 centimeters. So, option 2 is the correct answer. If the balancing point is obtained at 35th centimeter in a meter bridge, then the ratio of resistance in the gaps is, we have four options, 13:7, 11:9, 7:13, and 2:3. Let us draw a meter bridge. 100 centimeter length wire with resistances X and Y in the gaps. So for balancing condition, X upon Y is equal to L upon 100 minus L. Here L is the balancing length on the wire, which is given as 35 centimeters. Therefore X upon Y is equals to 35 upon 100 minus 35, which is 65. So 5 7s are and 5 13s are. Therefore, X is to Y is 7 is to 13. So, option 3 is the correct answer. The potential gradient along the potentiometer wire is 6 millivolts per centimeter. The balancing length for a cell of EMF 1.5 volt will be, we got four options, 150 centimeter, 200 centimeter, 250 centimeters and 300 centimeters. This is more of a maths problem, since for 1 centimeter the potential across 1 centimeter is 6 into 10 raised to minus 3 volts. Therefore, for X centimeters, the potential that needs to balance is 1.5 volts. Therefore, solving for X should be 1.5 upon 6 into 10 raised to minus 3, which is 2.5 into 10 raised to 3, that is 250 centimeters. So option number 3 is the correct answer. In a potentiometer of 10 wires, the balance point is obtained on the 7th wire. To shift the balance point on the 9th wire, we should, there are four options, decrease resistance in the main circuit, decrease resistance in the cell circuit, increase resistance in the main circuit, and increase resistance in the cell circuit. Let us draw a potentiometer of, say, this many wires. This is connected to a rheostat. So the rheostat here acts as an external resistance. Since we need to shift the balance from the 7th wire to the 9th wire, what we basically need to do is decrease the potential gradient. And in order to decrease the potential gradient, we should increase the value of the resistance, external resistance in the main circuit, and hence due to which the potential gradient of the wire would decrease and the balancing point would be obtained further ahead in the wire. And hence, option number 3, that is increase the resistance in the main circuit, is the correct answer. Potentiometer wire of length 1 meter is connected in series with 490 ohm resistance and 2 volts battery. If 0.2 millivolt per centimeter is the potential gradient, then resistance of the potentiometer wire is, let us look at the basic formula. V is equals to IR. So dividing by L on both sides, V by L is nothing but the potential gradient, is equals to I, the current flowing through the circuit, can be given as E upon R plus R dash, which is the EMF of the cell, and R is the potential resistance of the wire, and R dash is the external resistance, into R upon L. So potential gradient is given as 0.2 into 10 raised to minus 3 volts is equals to 2 volts of the EMF, R, which is the resistance of the wire, and R dash 490 ohms connected in series, into R upon length 1 meter. So solving this, we get R plus 490 equals 2 upon 2, 0.2 into 10 raised to minus 3 into R. Therefore, R plus 490 is equals to, this can be 100 times R. Therefore, 490 equals 99 R. Therefore, R can be approximated as 4.9 ohms. Therefore, option number 1 is the correct answer.